So our first objective is to construct this map delta n. So that is what we are trying to do. So notice that this is how the chain complex will look like. So we have short exact sequences here. So this is a short exact sequence going from an to bn to cn. Again, you should keep in mind that this phi of n is injective and this psi of n is surjective. Similarly, you have a short exact sequence here. This map is injective and this map is surjective. Then you have a short exact sequence here and this map is injective and this map is surjective. So this diagram continues downward and we have arrows going all the way in like this. So this is the chain complex A, this is the chain complex B, and this is the chain complex C. So we add 0 here. Now these two zeros can also be seen as complexes which just have 0 maps. So you could think of this 0 as a complex which just maps zeros going on like this. Similarly, this 0 could be seen as a complex with zeros going on like this. Now our objective is to define this map delta n. So we know that the map delta n, it basically goes from HNC to HN minus 1 A. So it goes from here and it goes all the way in here. So this is the map we want to construct. So let us do this. So say you have an element C here and we want to find the corresponding element here. So this C, say, gets mapped to 0 here. So this boundary we will denote as, say, since this is this D is associated with the chain complex C, we put C here. This is N here, so this is Tn here. So via this map gets mapped to 0. Now this is a surjective map because we are in a short exact sequence. So this C will get lifted to, say, some B right here. Now again you have this map differential here. Now this is in chain complex B, so we write dB in the top, and since here index is n, you have n here. So this B will get mapped right here. So we are taking this element B and bringing it here. But since this square is commutative, this element will get mapped to 0. This gets mapped to 0. So since this gets mapped to 0, you are able to lift it right here. So you are saying this B comes from some element A right here. And that is precisely what we are going to use. We are going to take this C and map it to this A we just talked about. So let us write this more concretely. So since we are in the homology group, so this homology group, you know, is nothing but kernel over image. So this is kernel over image. So its elements obviously have to be of the form this C getting mapped to 0 because they have to be in the kernel, and the coset is determined by the image. So delta n acting on C, this C is the element of the homology group, that's why we sent it to 0, plus the coset C plus the image of the elements coming from top above. So you had Cn plus 1 here, so the image falling from this group, and the map here would be this n plus 1 comes from this index, gets copied here. Similarly, this n gets copied here, and this arrow would be Tn minus 1. We are in complex C. So this is the left hand side, and the right hand side is precisely this element A plus image of coming from the here. So plus image of this map right here. Only thing we have to make sure is that there is agreement in this part. So that is, this phi n minus 1 takes A to precisely dn of B. So that is precisely what we used while lifting A up, because we said this was an injective map and this uniquely lifts up A here. So again, because this gets mapped to 0, since this is a short exact sequence, kernel is equal to image, so this is in the kernel, so it has to get lifted up to the image. So this is how we construct the map. But now we have to define that the map is well defined. So you have to make sure that this map actually makes sense. So we will do that in 3 steps. So we now talk about that this map A plus image, so this is independent of choice of B. So what it means is, say you take another B prime and corresponding to it you will obviously have A prime. So we have to show that if you choose another B prime, this A and this A prime are identical in the homology group. So that means that since you modulo out by kernel, being equal here means that A minus A prime is just the image of this map, image of DNA. So this is what we have to prove, because if these two just differ by the image, you modulo out the image, so in the homology group they will all be equal. So this basically comes from here. So this is what we have to show. So say you pick another element B prime, both B and B prime, they get mapped to C. So that means B minus B prime via map this psi of n will get mapped to 0. So B minus B prime gets mapped to 0. So therefore you can lift this map up, because we have a short exact sequence here. So B minus B prime going to 0, you can lift up to some element A1 here. On the other hand, via this map DNB, you again have B minus B prime right here. So this gets mapped to 0. So again, you know, this will automatically lift to A minus A prime, because corresponding to B prime we had A prime, corresponding to B we had A. So now notice this square is commutative, AN, BN, BN minus 1, AN minus 1. So on this side you're going from A1 to B minus B prime, from B minus B prime you're going to DN B minus B prime. This DN B minus B prime, this is coming from A minus A prime. Another way of saying A prime is, you know that D and B prime will get lifted to some A prime here. So because C, B prime is also getting mapped to C, C is getting mapped to 0. So you will have D and B prime here, and this will lift to A prime. So we have the square which is commutative. So since the square is commutative, this A1 goes to this element. So A1 should be able to go from here to this element also. But the problem is that phi n minus 1 here is injective. So since this is injective, it will only take A minus A prime to D and B minus B prime. And therefore this A1 gets mapped to A minus A prime. So the idea is this phi n minus 1 of A minus A prime is equal to dn B prime minus B. By commutativity of this square, this implies dn of this A1 gets mapped to A minus A prime. So that means they lie in the image of, so they lie in the image. So again, you know that Hn of A is nothing but kernel over image. So you have the image right here. In fact, we are talking about an minus 1. So let us make it specific. So you have kernel of dn minus 1 over image of dn. So you have A minus A prime that differ just by the image. So they are homologous. So we have been able to show that A plus image is independent of choice of P, because you took another B prime, this B prime gets lifted to A prime just as B got lifted to A, and then the only thing left is the commutativity of this square from an to bn, from an minus 1 to bn minus 1. The second part we show is that we have this A here, so we have A plus image of DNA, so this is right here. So we want to show that this gets mapped to 0 here, yeah, because that is what is the precisely the idea. It has to be in hn minus 1a, so that it has to be in kernel of dn minus 1, so this has to get mapped to 0. So the way we are going to show it is that we will show that this A plus image, this will get mapped to 0 right here. So since phi n minus 2 is injective map, this 0 will be 0 right here. So this is how we are going to show it. So first notice that you can go from this A, you can first apply dn minus 1 map. So from A you can go to an minus 2, and then you apply phi n minus 2. So go from here to here to here. So that is this map, first dn minus 1, then phi n minus 2, and then go from here, apply phi n minus 1 first, and then you apply this boundary map, which will be dn minus 1 but in complex P. So this follows from the commutativity of this square. But phi n minus 1a, this is equal to this differential. So instead of phi n minus 1, we just put dn phi a. Now you know that d square is equal to 0 in every chain complex. So this is 0. So this map is 0. And therefore, since this is an injective map, this map is 0 right here. So this is what we have been able to prove. Now the third thing for well-definedness we have to show is that if C lies in the image, then the A also lies in image. So notice that the homology groups for C with kernel over image. So similarly for A. So this is kernel over image. So if you start with some element in the image, you will get an element A which is also image. So if this C was lying in the image, then this A also lies in the image. So basically, if you are starting with 0, you are ending at 0, because we are talking about homology groups. Delta n takes homology group in chain complex C to homology group in chain complex A. So if you start in the image, you have to end up in the image. These images are the cosets. So basically, if you have 0 here, you should end up here. So this we have to show. Now since C lies in the image, so say C lies right here. So this is where C lies, and this is our corresponding A. So we are saying this C lies in the image. So this is C here, we have obviously correspondingly B here, and then we said that, you know, we agree this phi n minus 1 will take this A to this phi n minus 1a will take this A to this B here. This D and B would be same as this phi n minus 1 applied to A. So this is our initial setup. So this is how we define the map delta n. Now we are saying that C lies in the image of dn plus 1. So dn plus 1 comes from right here. So C lies in the image. So you are able to lift this C to some element right here. But again, we are focusing on this short exact sequence. This map is surjective. So since this map is surjective, this will lift to some element, say B1 right here. So you have this square, focus on this square is commutative. So this B comes by application of dn plus 1 to this B1. So this B is equal to dn plus 1 B, and that is precisely what I'm writing. So this D and B we are focusing on. So this D and B will be 0 because this D and B will be application of, instead of B you write Dn plus 1b, and you know that Dn plus 1 of B is 0, because in any chain complex this twice application of Dn would be 0. So this element becomes 0 right here. So you have to take A as 0. So corresponding A you take as 0. So therefore you can see that if you start C with the image, you end up at A as 0. Obviously if this D and B is 0, again this phi n minus 1 is injective, so this 0 will get lifted to A as 0. So the moral of the story is, if you start with C with something in the image, then this D and B becomes 0, and because of this map phi n minus 1 being injective, this A also becomes 0. So A becomes 0, that is A lies in the image. And by 1, you could take any other choice. You could take any other choice of B. It will still give you A and the corresponding A primer homologous. So by A is 0, we means A is 0 here. So you have 0 plus this image. So that is what we mean. So A lies in the image. So it is 0 plus image of DNA, which means it lies in the image. So that is the story. Now we still have to check the exactness of delta n. So this is how the sequence looks like. So we have to check exactness of delta n. So 4 things we have to check. First we check that kernel of delta n, this kernel here, contains image of this map. Then we check the opposite direction. So you are checking exactness right here. Now kernel of delta n is contained in the image. So here you have to say kernel of delta n is exactly equal to image of this map hn phi, and similarly here kernel of hn phi, here hn minus 1 phi is exactly equal to image of delta n, and that's what we, so kernel of hn minus 1 phi contains image of delta n, and kernel of hn minus 1 phi is contained in the image of delta n. So we are trying to establish equality here. So these are the 4 cases we now need to check. Now few words about this map hn phi. So this map hn phi is just exactly like the map phi, but it acts on the kernel. So notice again, say for example HNB is nothing but kernel of Dn over image of Dn plus 1. So we are talking about Dn right here and Dn plus 1 coming in here. So you're trying to find the homology group right inside Bn, taking kernel of Dn and modulo out image of Dn plus 1. So map phi n basically acts only on the kernel of D of n for this hn of phi. So basically you're just borrowing from this map xi of n. So now let us do a proof that kernel of delta n contains image of hn of xi. So you start with this. So say hn xi takes this B to C plus the coset, corresponding coset. So you have B plus image of Dn plus 1 to C. So this B here gets mapped to this C right here. But if you apply Dn to it, this will get mapped to 0 because we are talking about homology group. This map is acting on the homology group, and this numerator here is kernel. So this B, when Dn you apply to it, it will get mapped to 0. Now since this gets mapped to 0, so this is 0 since it lies in the homology class. So since this B gets mapped to 0, now our construction is from C you go to B, and from B you apply Dn, and then you have Dn of B is equal to phi n minus 1 of A. So this dn of b is 0. So this phi n minus 1 is injective map. So this a will also be 0. So you have delta n applied to the c. This gives you, so this I'm copying right here. This gives you a plus image, but this a we just showed is 0. So you can see that the image of hn phi lies in the kernel, because if you apply delta n to the image, you get 0 as we have just shown. So now we prove in the other direction. You start with the kernel. So delta n applied to this C plus image map, because we are going from homology group, is equal to 0. So this is equal to 0. So that precisely means nothing but A lies in this image. So that is why it is 0. So you have the same series of maps. From C you have B, and from B you have this map phi n minus 1a is equal to, so you have you combine both these maps here, and then you have a here. That is our standard construction of getting a. So we are saying a is 0, so obviously this phi n minus 1 is an injective map, so this becomes 0 here. Now since a lies in the image here, you can lift a to a1. It lies in the image of this dn, so you lift a1 here. So this square is now commutative. Yeah, so in particular, so in this square in particular, you can go from a1 to a to 0, or from a1 you could go to b and then 0. So you have dn of this b minus phi n of a1, this is 0. So both of them, because of the commutativity of the square essentially. Yeah, so this phi n of a1 is equal to b if you apply dn to it. So you could go from a1 to a to 0, or you could match up a1 and b. Matching up a1 and b means b is equal to phi n a of 1. But since we are just focusing on this particular square, so that means when dn is applied to it. So that is pretty much it. This is equal to 0. Now to the same map, if you apply psi of n, so you have b minus phi of n a here. So you have commutativity here, so you apply dn to here, you got 0. But if you apply psi n to it, so say you apply psi n to it, the same map, you get psi n of b minus psi n phi n a1. So I'm just taking the psi n inside. So first notice that if you apply phi n first and then psi n, you get 0. Yeah, because image of this lies in the kernel of this map. So image of phi n lies in the kernel of this map, so this becomes 0. So this term is 0. That's what we are saying. And the way we construct b is that b is equal to psi n of c is equal to psi n of b. So c is equal to, so this is by our construction. That's how we constructed it. So this gives you c. So now to this b minus phi n of a1, you apply this hn phi. So hn phi is nothing but same as applying phi n, but to a limited set of bn. So rather than applying phi n to all of bn, you just apply it to the kernel of dn, because we are talking about the homology group. So hn phi is nothing but a restricted map of phi, and then you apply to it, you just have to copy the same formula above right here. So this will be equal to c, and instead of 0 you write image of dn in the chain complex c. So you can see that you started with this thing getting mapped to 0, and that implied that this you get this again as the image of the map hn of phi. So you can see kernel of delta lies in the image of Hn of psi. Now we come to third part. We are right here now. Now we have to prove exactness right here. So that is kernel of this map contains the image of this map. So you just follow the definition. So we are going to apply map this Hn minus 1 phi to this delta map. So delta map is our standard map here, delta n c plus image. So that is what our delta n map is. You apply Hn minus 1 phi to it, you should get 0. So Hn minus 1 phi is nothing but again this map phi n minus 1. So you apply phi n minus 1. So you are applying phi n minus 1 to both sides. So you have phi n minus 1 coming right here, and you're applying it to this map. So phi n minus 1a you get here, and then phi n minus 1 you apply to the image, you get image in dn. So phi n minus 1a you apply to plus some image map, yeah, phi n minus 1 which acting on the image of some element here from an, acting on the, so for example this acts on the image here, this will take it to some image element right here because of the commutativity of the square. So this could get lifted here, this could come here and then down here. So because of commutativity, image gets carried to image. So this image here will get carried to image here, and this we are just carrying as such. So again this phi n minus 1a, you look at it here, phi n minus 1a, this is equal to image, again boundary or differential of some element b here. So if you put d and b here, if you put this right here, so this plus image, so this will get absorbed, so this gets absorbed in its image element here, so this is equal to 0. So this is how you get the kernel. Yeah, obviously because Hn minus 1 itself is nothing but kernel over image, so you will modulo out all the image. So when you say Hn minus 1 phi, you will modulo out all the image, get 0. So the last thing we need to show is kernel of Hn minus 1 phi is contained in image of delta n. So just the reverse of this. So you start with the kernel. We now prove the last part, that is kernel of this map lies in the image of delta n. So let us start with the kernel. So say a, so obviously we are starting from here, this a here with the help of this map gets mapped to 0, that is a plus image lies in the kernel, it lies in the kernel of this map. So that is a gets mapped to 0, so 0 means it lies somewhere in image of dn p, because this homology group is nothing but kernel over image. So you modulo out image, image is 0, that is means a getting mapped to 0 means that this a, if you so kernel of Hn minus 1 phi, so phi again is this Hn minus 1 phi is nothing but just the map phi n minus 1 restricted to the kernel of this map. So that means you have this element a here, if you apply phi n minus 1 to it, you get a 0. So a, it goes to 0, this is the map, this is the map phi here. So this is the map not psi but phi here. So this gets mapped to 0. So that it lies in the image. So if it lies in the image, you should be able to get an element b here which gets mapped to 0 here. So now you just put this element, take an element c and cn which is equal to psi n of b, and that is the end of the story. Now we will just show that this c will map to 0, and that would imply that we are lying in the image of delta n. So let us see this. So essentially what we want to show is that C plus any image coming from here is in Hn of C. Again, Hn of C is nothing but kernel over image. So basically we are talking about kernel of Dn of C. So we want this C to get mapped to 0. Only then it will lie in the image of delta n. So image is landing up right here. So let us see this. So we want this, you apply dn to it, it gets mapped to 0. Now you can see directly from here, basically we are going to, instead of C, we are going to go all the way back to A, and A you first apply this phi n minus 1 and then you apply psi n minus 1, you will get 0 because it's a short exact sequence. All the elements here get mapped 0 here. But let us see this. So you set C as psi n of B. Now we have to check that C lies in Hn of C. So that is, we are saying that kernel lies in the image of delta n. So it lies in the image here. So you put dn on C here and we have to show this is 0. That is the definition. Now going from here to here, we can say instead of C you write phi n of B. You have written this. So you say from B you take it first this route, and this route is same as going this route and this route. So you're saying first apply dn of B and then psi n minus 1. But dn of B is nothing but phi n minus 1 A, because that's what we have here. So dn of B is nothing but phi n minus 1 A. That is how we lifted it up, and you compose these two maps, you get 0. And so this does lie in the Hn of C, and therefore this C does form the part of the so this C lies right here, and this C is precisely what is getting mapped to A here, and this A is getting mapped to 0 here. So we showed if A gets mapped to 0, you can lift this A to C via this map. You got A, it got to 0, or 0 instead of 0 you could write 0 plus image of dn. Then you lift it to B, and this C you constructed essentially a psi n of B, and we got this C, but then we just needed to check this C does lie in Hn of C. So that is, this C does get mapped to 0, only then it will be part of the homology group. So that is the end of the story. So now the thing remaining is checking the exactness here. Exactness basically here. So we have to say first kernel of this map contains the image. So kernel of this map contains the image of this map, and then kernel of this map is contained in the image of this map. So basically we have to show that there is exactness here. Kernel of Hn psi is equal to image of Hn phi. So let's do the first one. Kernel of Hn psi, this contains this map, the kernel of this map contains the image of this map. Now this is very simple because we know that Hn phi is nothing but a special case of, it's just a restriction map of phi. Yeah, this is nothing but restricted map of phi. So phi acts on all of, so if phi acts on all of Cn, in Hn phi the phi acts on just that part of Cn which gets mapped to 0 under map dn. So that is a definition of the homology group. So Hn phi is right here, Hn psi is right here. You compose them, it's basically composing these two maps. First apply phi and then apply psi, and this is nothing but a short exact sequence. So when you compose these two you get a 0 map, and that's why it is 0. So this part was easy. So kernel of Hn phi contains image. Now the second part is slightly more involved, that kernel is contained in the image. So let us see this. So we start with the kernel. So you start here and we want to end up right here. So if an element is here, that means it is element eventually here. So say this, you apply this map h and psi on some u and it gets mapped to 0. So you have u here and it gets mapped to 0 here. So 0 means that it has to be part of image of dn in the complex C, because h and c is nothing but kernel over image. So this is kernel over image. So 0 means it is getting mapped into the image of some element dn of dn plus 1 of C. So this u, you apply phi n to it, you get phi n of u, but this phi n of u is basically 0. That is, it is equal to image of some element v via the differential map, because h and c is equal to kernel over image dn plus 1. So this comes from some v right here. So this u comes from some v right here. Now this phi n plus 1 is onto map. So this is a surjective map because we have this short exact sequence from 0 to a n plus 1 to b n plus 1 to c n plus 1 to 0. So this v lifts up to w right here. So v comes from some w in bn plus 1. So now you have a commutative square. So this square right here is commutative. So phi n of u, this u going from here, this is same as this w. So phi n of u is equal to, you first apply you first apply this map and then you apply this map on w. So basically this u comes from v, which comes from w, and there is a commutative square here. So this we can rewrite as phi n of u minus db n plus 1 w. I'm rewriting this. So this equal to becomes this equal to 0. So this u minus db n plus 1 w lies in the kernel of xi n. So lies in the kernel here. So that means you can lift this to some element t here. So this comes from t in an. So now we have the map. You have t gets mapped to u, and then this u gets mapped to 0. So this is the map. The only thing now remaining is that we have to confirm that this t does lie in the hn of a. So since hn is equal to kernel over image, this kernel of dn and image of dn plus 1. So we have to show that if we apply dn to t, then it should be 0. So if you apply this dn to t here, you should get 0 right here. So we will prove this. We will show that this t actually goes via here. In bn minus 1 it gets mapped to 0, but then this phi n minus 1 is injective, so this map is 0 here. So you first apply dn and then phi n minus 1. So this is equal to applying this map first, phi n, and then dn in this complex b right here. So instead of going from here, you're going via here. But this phi n of, instead of phi n of t, so instead of phi n of t, you know that this phi n of t was essentially this, yeah. So this is what we lifted to t right here. So when you apply phi n again, you should get this thing. So phi n of t would be, so phi n of t now becomes, is this map, and then you apply dnb to it. So apply dnb to it, so you get u dnb, then so again you're applying dn here and then dn right here. So this is d square, this will become 0 automatically. Now you are left with this dn of u, but dn of u is 0. This is how you started with. Yeah, so dn of u is, so dn of u is 0, simply because u lies in this homology group, which is nothing but kernel over image. So kernel same index, image comes from higher index, so obviously if you apply dn to it, it will become 0. So that is how you get 0 here. So we have shown that this t gets mapped to 0. Now you have, say, phi n minus 1 is injective, so it is 0 here. So it does lie in Hn of a, and therefore we have the required result that t does get mapped to u, and then this u is getting, so if u gets mapped to 0, you can lift this u to t, and that is how this, so again this map phi is nothing but this restricted map of phi n. So basically for all the proof techniques we have followed some simple logic. So first thing you need to keep in mind is short exact sequences. So there are injective maps and surjective maps in a short exact sequence. This map is injective, this map is surjective. That's what we have used. This is number one. Number two, we have used these HNs. So you have to remember this HN of a chain complex. This is nothing but kernel over image, and image is always one index more, kernel is the same index. So this we have used, and then this is nothing but the same map as this, but now restricted to, say, kernel of dn. Instead of the entire complex, it is restricted to kernel of dn. So ideally this map would act on entire of bn, but now you just restrict to the kernel of dn, and that is pretty much it. We now talk about naturality between the two chain complexes. So naturality means natural transformations. So you know that each of these Hn is a functor, and we are talking about natural transformation between functors on different complexes. So let us see this. So first we draw the first chain complex. So you have, say, ai here, bi here, ci here, ai minus 1 here. This goes all the way, this is coming, so this is the chain complex corresponding to, say, A. Then you have bi here, bi minus 1 here, and this will go so on. So this is the chain complex B, and then you have chain complex C. You have ci minus 1 here, and then these are short exact sequences. 0 is here, then similarly here. So this is the chain complex we have drawn several times. You see the indices are decreasing. These are the standard differential maps. Now we draw the second chain complex. So let us draw the second chain complex in a different color. So this is, say, A prime I, B prime I. This is the second chain complex. So again, just like the first chain complex, everything we have to draw. B prime I minus 1, C prime I minus 1. Keeps going like this. So this comes from the chain complex A prime. This corresponds to chain complex B prime. This corresponds to, say, chain complex C prime. So again you will have the arrow coming out of it. All of these are again short exact sequences. So we put 0 here, 0 here, again a 0 here going in, 0 here. So now let us focus on the white diagram. So for the white chain complex, we know our standard trick. Let us write down the white chain complex in red. You had C here, you have C here in Ci, this you lifted to B here, and then you had the corresponding A here for the delta n map. Yeah, and then you said that you're going to glue these together via map dn. So you put your dn of B was equal to phi n minus 1 of A. So this is what was our construction on the white figure. Now we do the same thing on the yellow figure. Again, you have C prime here, you will have corresponding B prime here, and you have corresponding A prime here. Now we draw the map between two complexes. So drawing the map between two complexes means that we have map from, so let us draw these maps in green. So you have this map here from AI to AI prime, AI minus 1 to A prime AI minus 1. Similarly, you have map in B, and you have map in C. So what does naturality mean? So say you label this map as HI, then we are worried about this map because in this map we have we are gluing this DNs together. So here we have DN of B prime here, so this B prime comes here, so you glue this together. So A prime are glued together via this map, then DN B prime, and then C and C prime. So put this as HI, so put this as GI minus 1, and you have here, you put this as FI minus 1. So we have three maps which we are focusing on. This map which carries A to A prime, this map which carries C to C prime, and this map which carries D and B to D and B prime. And this is precisely what naturality is. So naturality is that Hn of H, so Hn of H means, so instead of Hn I should write Hi because we are focusing on I here. So Hi of H basically will carry C to C prime. So it will carry C plus whatever image comes into it. So image which will come into it will be Di plus 1 in category C or chain complex C. This will be equal to, obviously you guessed it, C prime plus image of Di plus 1. Now we are in chain complex C prime. That is pretty much it. Similarly, you talk about this and then you have to talk about A and A prime. So here is map F, but here we are talking about Hi minus 1. So it will map as F, and what will this do? This will take this A to A prime. This A will be taken to A prime, then you just add the image map, image of so this is I minus 1, so Di is coming into it. Di, here you have A prime and here you have A. Image of Di of A. And the correct way to see this is in terms of natural transformations, but this is what naturality means. You carry C to C prime in these chain complexes, you carry A to A prime, and these maps which I have marked in green are given to you. And that is pretty much it.